Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We are delivering lecture on X-ray crystallography and solid state chemistry. This is our 11th lecture on X-ray diffraction. The first slide in this lecture, we talked about these problems a bit in the last lecture, that is 10th lecture, but we didn't finish it. Therefore, I take it again. This is some problem what we discussed in earlier lecture. This is a spectrum of iron target. We are asked to label it. We have been seeing the spectrum, iron spectrum, X-ray spectrum of target metal. But now labeling it, what does it mean? It does mean that we have to identify this peak, these, and other this. And then also, do not forget, then also we have to identify the x-axis and y-axis. You know, that in x-axis we always plot the wavelength in Armstrong, and in y-axis it's an arbitrary intensity. So this is arbitrary intensity. This is what we call the wavelength in Armstrong. And then what is this point? This is short wavelength limit. In all target spectrum, we see this short wavelength limit. This is the short wavelength limit. And this is continuous white radiation. And then I'm sure you know what this peak means. This is iron K beta, iron K beta. This is the iron K beta. And then what is this one then? Iron K alpha 1. And then this one is iron K alpha 2. So now this is the labeling what the problem is asking to us. Next, this one. This is another spectrum. It's called absorption spectrum of lead. And we are supposed to, again, label this as fully as possible. Then, we are coming to what is x-axis and what is y-axis then. You remember we call mass absorption coefficient. The unit is centimeter square per gram, and this is as usual the wavelength in Armstrong, and this peak we call it K absorption age. That means this is K absorption age of lead. And then this where we go, this is another peak, which is L absorption of lead. And that L1 absorption, we call it L1 absorption of lead. This is L2 absorption of lead, and this is L3 absorption of lead. Now the question comes, what about M absorption, N absorption? If we continue this peak, we will see similarly N absorption spectrum and M absorption spectrum. Next problem is this one. Using the following data to determine which of the following radiation would produce X-ray fluorescence in iron. That what is the question to us. Okay, then what we see, the data is given chromium K alpha wavelength, copper K alpha wavelength, K absorption age of iron. We are to find out which of these wavelengths will produce X-ray fluorescence in iron. And that is what it is, if you look to it, that it is copper K alpha will produce X-ray fluorescence for iron. Since chromium K alpha is too high than that of absorption age, so therefore copper K alpha will will produce X-ray fluorescence in iron. Okay, come to this one. What is the data? What is this problem says? Using the following data, select the metal which should remove cobalt K beta 1 from the output of cobalt X-ray tube. That means we will have a output of cobalt X-ray tube like this, and we are asked to that which filter we use to remove this one. So the following data is given: copper K beta 1, the wavelength is this. K absorption age of nickel is given. K absorption age of iron is given. So you see the K absorption age of iron is slightly higher than that of cobalt K beta 1. Therefore, K absorption age of this one is higher a little bit, and therefore iron will remove the cobalt K beta 1 of cobalt target. We come to this then. It says, why is human tissue transparent to X-ray but not to visible light? Choose appropriate answer from the following. What is the answer? X-ray fluorescence X-ray causes fluorescence. One answer. Second answer is visible light has a wavelength longer than that of X-ray. Third answer is visible light is reflected by human tissue but not X-ray, not X-ray. Fourth answer is solid penetrate more easily by short wavelength radiation than by long wavelength radiation. You see, all these statements are correct, but according to the question, 2 and 4 will be likely answer for this question. 2 is visible light has a wavelength longer than that of X-ray. Therefore, visible light cannot visible light for human tissue transparent to X-ray, but not to visible light. Similarly, solid can penetrate more easily than short wavelength than that of longer wavelength. This is a problem I took from a book, and I discussed with you about this problems, how to answer this using the learning we had for last couple of lectures. Now we are talking about X-ray diffraction methods. This is what it is. So this figure shows what is X-ray diffraction method. We will have experimental method like this. We will have a source of incident X-ray and then sample, and then we have to collect X-ray diffracted rays, a detector. So we need an X-ray source, we need a sample under investigation, and a detector pick up the diffracted X. These are the 3 points we have in our basic requirements for X-ray diffraction techniques experiment. Okay, if we go to this a little bit, we'll see that within this broad framework, 3 variables govern the different X-ray techniques. One is radiation, another is sample, and third one is detector. Radiation means we must have to have a monochromatic or of a variable wavelength. This we must have to have. Sample, we can have single crystal, we can have powder, we can have a piece of solid. Detector, we can have radiation counter or photographic film. Let me explain a little bit here. You see, wavelength, we said fixed or variable. Which are the simple, that these powder or single crystal, there we used fixed wavelength. Do remember, there we used fixed wavelength. What about counter? We said detector could be a counter or film. This would be our variable. So for powder, counter is diffractometer. If we go for film technique, we do have device sharer camera or linear focusing camera. For film technique, these two cameras we use. For counter method, we use diffractometer. For single crystal, similarly, we can use film technique or count. Film technique, what are the method we have? Rotation oscillation, Weisenberg, precision Berger. These photographs we take by film technique. And then counter is automatic diffractometer. But for variable wavelength, when we take our sample solid piece, it's only film. And the method we call is Lau method. So these are the basic diffraction methods for studying solid materials. Next we go. You see, it is we know the X-ray is having short wavelength, and it is very, very health hazardous. So we have to take precautions in the X-ray laboratories. Early X-ray users suffered a lot for X-ray burns, which were difficult to hit because they didn't take enough precautions, or probably they didn't know how to take precautions, so they didn't have possibilities of taking precautions, or probably there were no data about this health hazards of X-rays in early days. So repeated intermittent doses, what causes dryness or overgrowth of the skin or brittleness of bones. This were not realized in earlier days. So many pioneer users died prematurely of cancer when working in the X-ray laboratories. Well, then later people started extensively and on human populations and animals, what happens when ionizing radiations have been absorbed. This is biological effect of ionizing radiation, and this basically a chemical in nature. So this formation of ions, free radicals and excited molecules are caused by these ionizing radiations. Species such as this, or proton, or OH radical produces chemical change in cell material using deformation or malfunctioning of the cell. Malfunction of the cell from chromosome damage due to exposure of X-ray and ionizing radiation, and this damage is generally not immediately felt. Take a rather long time to see the damaging effect felt. Therefore, what happens then? With this study, modern commercial equipments are designed and marketed with considerable taking care of health hazard and other high voltage safety precautions. So it is very important for personnel using X-ray that they constantly are on guard against accidental exposure. How do we use dose of units for radiations? So it is equivalent dose. Do remember that we have different ionizing radiation produces different amounts of biological damages. So to make a uniform, we call it dose equivalent. So which is dose equivalent H, which is equal to DQN. Here Q is a quality factor related to effectiveness of radiation for causing biological damage. N is a modifying factor used for the distribution of the dose and space in time. So Q and N are dimensionless. But, for example, for beta particles, X-rays and gamma rays, Q is unity. Whereas alpha particles and protons up to 10 million electron volt have a value of about 10. And the unit of unit we call H Unit of H is CBR, with S, the capital S, lowercase b. Well, biological effect of radiation. Number of factors influence that. For example, the presence of certain substance at the time of exposure. An example, we can take oxygen. Oxygen increases the amount of damage. If we have oxygen, atmosphere at the time of exposure, oxygen increase the damage dose. Okay, time distribution of the dose. How long we are exposed, that is also. A single dose produces more damage than several smaller intermittent doses. But what about the user? The age of user also affects a hell lot. Adults have more resistance than infant and old people. What about amount of body irradiated? The finger can tolerate greater, but that means a part of a body can tolerate a greater dose than the whole body. The typical cell irradiated, what are the cells? Skin cells, sex cells, bone marrow are most vulnerable for this hazard. So there is a table here which shows the limit in UK per calendar year, and the unit is millisievert. Okay, what is this? Worker, trainee, or any other person. Worker having aged over 18, whole body limit is 50 millisievert. An individual organ except eyelids, 500 millisievert. For eyelids, limit is 150 millisievert. Trainee below 18 years, their whole body exposure limit is 15. Mind it is in this UK data. I'll come to it again. And 150 for individual organs and 45 for eyelids. Any other person, that is, say, children or an old person, whole body limit is 5, and individual organ is 50, and eyelids is 50. What I say, I come back to that. It is a limit regulation for UK. You know, every country must have a limit for dose limit for any calendar year, and that will differ country to country. Now, radiological protection. How do you protect us while working in X-ray laboratory or any radiation, including laboratories, whatever it may be? That is controlled by International Commission of Radiological Protection, ICRP. Many countries follow ICRP's legislation. Some probably have got a higher limit, and they also do follow, but their limit may be a little bit higher. What we can do to protect the X-ray laboratory, we can made up the floor, walls, doors, ceiling, etc. with materials and thickness to prevent X-ray to persons in the night wearing rooms. That means their own X-ray rooms or any other radiation rooms, the door, ceiling, fans. We made it with such materials and thickness that it could prevent or it would absorb X-ray to so that it doesn't go to night wearing rooms. Another way of interlocking X-ray generator with the door. That means whenever if the door is open, the X-ray or radiation machine will not energized. So you have to shut down the door, and then it will be energized. You can install warning light near the machine or outside the laboratory, so people should know that this in this room now X-ray or radiation experiments are going on. Operate X-ray generator from outside a ray-proof room. Ray-proof room. Remember, we can operate. You will see in very many medical X-ray that the person who is working is shielded in the room, and from the room remotely is operating the X-ray generator. Totally enclose the machine with heavy absorbing material so that X-ray tube cannot be energized until the shielding is correctly placed. So I have a shield for our machine, and then unless and until I shield the machine correctly in place, the machine will not be energized. Ensure the windows of X-ray tubes are fitted with ray roof shutters. You will see that almost all commercially machine having windows with ray roof shutters. And lastly, you have to monitor regularly inside and outside of the X-ray laboratory whether any leakage is going on when the machine is on. Let me say interesting and also incident. While I was working in the X-ray laboratory, one of our worker who just protected the chips we get from putting it in the lab apron, he just took that one and put in the window of the X-ray machine and on it. And doing that, this one, regularly one has to monitor this badge. So that was sent to International Commission for Radiological Protection. And immediately a telegram came back saying that, did the person yet alive? Something like that. So don't make any foolish attempt while you are working in the X-ray lab. This is a warning. Well, radiation in perspectives, what happens? We do get natural radiation other than the man-made radiation, that is other than medical and industrial uses of radiation or even testing of nuclear power. Other than this, we do have some environmental radiation. And again, I come to UK limit. UK's limit is 2 millisievert per year. The average dose arising from natural background in the UK is about 2 millisievert per year. But then this table says what are activities, how we are affected with this radiation. So radon in the atmosphere has got about 0.8 millisievert per year, medical X-ray 0.5, ground and buildings from where we get about 0.38 millisievert, food and drinks for about 3.7, and cosmic rays 0.31. Other than this, testing of nuclear weapons 0.001 millisievert per year, miscellaneous sources for luminous watches, TV sets, etc., about 0.01 millisievert. Air travel, when you travel by air, we do get radiation also about 0.008 millisievert per hour, nuclear power 0.003. I took this scale that a dose of 10 sievert delivered to the whole body for a few minutes proves fatal. But again, 3.5 sievert administered to whole body for a short time, resulting in 1 in 2 chances of death. But the same dose could be tolerated if accumulated over 1 year. Doses of tens of sievert to small areas of the body are generally used in the radiotherapy to kill cancerous growth. I again mention here that personnel working in X-ray and other ionizing radiation must constantly be on guard against accidental exposure. That is a very important thing when working in X-ray laboratory. We have been talking about hazard and radiation damage, etc. Now we have to talk about Lau equation and Bragg equation. Next two slides will be on Lau equation and Bragg equation for X-ray diffraction. That we will take in the next lecture. Thank you for your attention in the 11th lecture of X-ray diffraction by crystals. Thank you very much.